Hello everyone, my name is Ivan. I'm an analyst at Yandex self-driving car department, and I'm helping our engineers to build datasets. And our today's agenda is crowdsourcing for computer vision with examples from self-driving cars. So today we are going to discuss the following points. Why are ready-made datasets not enough? Then we are gonna dive deeper in details about labeling for computer vision with examples from self-driving cars. And we are going to discuss a little bit about collecting data for computer vision problems. So a few words about ready-made datasets. I think everyone who is dealing with machine learning problems knows that there are a huge amount of open datasets with labeled images, labeled videos, labeled any type of data. For example, ImageNet or Coco or some other dataset. And of course, when you are trying to build a baseline solution for some ML problem, you can use open datasets. But let's imagine that our goal is to train a model that will recognize objects on the streets. Let's say the objects will be, for example, pedestrians, cars, animals, traffic signs, traffic lights, and anything we can find on simple road situation. And can we take an existing open source dataset to train our model? And what can go wrong? These are the questions. The answer for the first question is, of course we can, until, and then comes the answer for the second question. What can go wrong? For example, we can train a baseline machine learning model for solving our problems, and we can reach some accuracy in detecting and classifying objects on, for example, images, and then we can get no profit. I mean that we can reach some numbers and no profit more. What is the problem here? Sometimes it means that our dataset doesn't contain data which reaches our road circumstances, which we want to check, for example. And this is where we come to the problem of collecting our own data, which will describe the situations when and where we are going to use our machine learning solutions. And the following points, which are presented on this slide, are some kind of best practices for data collection, for collecting our own data to build datasets which will face the problems we are going to solve and which will face all the requirements for our situations. First of all, we should describe all necessary conditions, not just ask to make a video or to make a photo or something like that. Necessary conditions means, for example, make some photos with rainy weather, with snowy weather, with misty weather, with a huge amount of cars on roads, with a small amount of cars on roads, and so on and so forth, with red lights, I mean traffic lights, with green traffic lights, and further and further. When you make your own datasets, don't forget to use post-verification of collected data. It means when you get the first draft of the data you've collected, don't hesitate to check it, whether it faces all the circumstances, all the requirements you want to take in account in your solution. If you are going to use, for example, you are going to use crowdsourcing for data collecting, this is a good solution sometimes. Not every time, but sometimes it's a fine solution. You use a crowdsourcing platform for this. Target tasks to mobile users, not only personal computer users, because collecting data nowadays in the 21st century is 99% can be solved using mobile phones, photos and videos, absolutely. And try to look for external services to automate some steps and save some time and money. It means that, for example, if you have a video and you want to break into separate frames, don't try to write your own code. Don't try to find your own utilities to separate your video sequences and frames. Find something already done. Don't waste your time. Don't waste your money. Okay, this was a very little discussion of data collection and why do we need our own data sets. And now imagine we already have some data set and we want to label it. This is a little video introduction to Yandex self-driving cars. This is where I work and where I help our engineers to solve some machine learning problems, making data sets for them. And I think 2 years ago, Yandex participated in Consumer Electronics Conference in Las Vegas. And this is how self-driving car without any person in the driving seat operates. Just an example of the real life usage of crowdsourcing data labeling and further usage of this labeled data. So, how does labeling pipeline in self-driving cars works in general? Cars drive along streets and collect data using different sensors. Sensors can be, for example, images, LiDAR clouds, radar clouds, and so on. We just extract the data from this self-driving cars, right? And find cases in this data which we find the most interesting. For example, crowded places or places with a huge amount of cars or places with a huge amount of traffic signs or anything you can find interesting. Then we prepare this collected data for crowdsourcing platform and give the performers in this crowdsourcing platform some tasks in order to get the answers for the questions, for some tasks. The tasks can be, for example, find every person on image, find every car on image. Is this person a child? Is this car a truck? Any question you may be interested in. And after we get all the data labeled, we just collect it in one place, use it for machine learning, for learning our models, deploy it on cars, drive once again, extract cases once again, label the extracted cases once again, learning, writing, extracting, labeling, learning, writing, and so on. This approach is called active learning. This is when you are trying to find the cases which you find most interesting and where your models, let's say, not fail, but these are the cases where your machine learning models are not good enough for you. Label them, use for learning, and so on and so forth, and so on and so forth. And for example, here we have a video of some success of this approach, and also this is an example of how important circumstances of the situations where you collect data can be, and why you really need your own data sets. Please pay attention. This is the video of the same LiDAR cloud, but on the left side we have a raw LiDAR cloud without any filtering, and on the right side we have a LiDAR cloud which is filtered and there is no snow, or let's say no snow, like not absolutely no snow, but much less than on the left side. Let's have a look. So as far as you can see here, the lighter cloud on the right side of the video is much clearer and not as dirty as on the left side. Okay, these were some general words about how labeling pipeline is working in our self-driving cars problems. Let's have a look in details on how we label transport and what problems are we trying to solve, creating our own labeled transport data sets. So the pipeline looks like it is presented on this slide. First of all, we usually use decomposition. Decomposition means that if you have some comprehensive, complicated problem, you should separate it in some easier tasks in order to get more control on every step of your labeling process, in order to get different performers on every step of your problem. And it is just easier and faster and huge amount of other advantages. So the pipeline looks like this. First of all, let's imagine that we are trying to find every car on camera images and classify them. And on the other side, we are trying to find cars in lighter clouds and classify them. So we have two types of data, images and lighter clouds. And we want to find every car on images and lighter clouds and classify every car there, every transport type. So the pipeline looks like this. First of all, we show our performers images and ask them to answer the question, what objects are presented on image? And they just put answers in checkbox. People, traffic signs, transport, animals, anything else. Then we take all the images where transport is presented and divide our pipeline in two branches. On the left branch, we have 2D labeling pipeline. It means that on the left branch, the tasks for image labeling are presented. And on the right branch, we have 3D labeling. It means lighter clouds. So let's have a look at 2D labeling branch. First of all, we ask our performers to find every car or every truck or every bicycle or every motorbike or any type of transport on the image, and just to use bounding boxes in order to detect accurately the location and size of every transport object, just like it is shown on this image. Quite easy. When we get answers for this task, we have the next step, which is called validation. What does it mean? We take answers for the 2D labeling task and ask other performers to check whether this labeling is correct, beautiful, fine, and faces all the requirements we asking to face. This is called post-verification. This approach is called post-verification. You ask performers to check other performers. Helpful thing. And when we get all the tasks, all the images labeled and validated, if it is validated, I mean, if it faces all the requirements, because when it doesn't, we ask to relabel it. And well, it's like a circle. When we get all the images finally labeled, we ask other performers to classify every transport which is outlined with a bounding box. Just just choose the transport type: truck, car, bicycle, motorbike, and so on. So after the left branch is fully done, we have images with every transport object outlined with a bounding box and classified. And now let's have a look on the right branch, which is about 3D transport labeling. It is something the same, but we do not use only images here, but also LiDAR clouds, 3D LiDAR clouds. The task we are asking our performers to do is just to outline every transport object in LiDAR cloud using a 3D rectangle, a 3D box. That's all. The difference from image labeling is just that there are 3 dimensions in these tasks. And when you are trying to label 2D, there are 2 dimensions. And after we get all them 3D, as far as you can see on this slide, after labeling, we also have validation. So the first performer finds every transport object in LiDAR cloud and outlines it with 3D box. And the second performer just checks whether it is okay. If it is not, he tries to fix it. If it is okay, he just says, okay. And when we get all the transport outlined with 3D boxes, in LiDAR clouds, we just merge 3D and 2D results. And what do we have as a result? We have LiDAR clouds and images with labeled transport objects. And labeled means we have location, size in 3D and 2D domains, and we have classification, and we know what is the type of this transport. So few words about quality control we can use here. This is just an example. You can use any approach you like, but for example, you want to compare 2 answers for, let's say, 3D transport labeling. It means that you have 2 sets of bounding boxes, of 3D bounding boxes for the same LiDAR cloud, and you want to answer the question whether these sets are the same or quite the same or just different. Of course, you can have to calculate some quality metrics. For example, it can be precision and recall, just something everyone uses when solving machine learning problems. So you just take 2 sets, compare every bounding box with every bounding box from another set. If the comparison function reaches some threshold number, you can say that, okay, these 2 bounding boxes are the same. If not, they are not the same. And then calculate precision and recall and answer the question whether all the sets in, whether all the objects in 2 sets, for example, first question and the second question, are the same or quite the same, face all the accuracy thresholds or not. But when talking about 3D labeling, we do not only label objects, some compact and I don't know, just objects. Okay, something, but we also segmentating 3D clouds. What does it mean, segmentation? We have already seen the example where the car drives across the street and there are snowflakes in LiDAR cloud. On this slide, we can see an example of the same situation. We have a road here, and with white color snow points of LiDAR clouds, which are reflected from snowflakes, are segmented. So we are asking our performers not to find some objects in LiDAR cloud, but let's say classify every point in LiDAR cloud in order to find something which we are interested in. For example, snow, mist, rain, dust, anything that can be harmful for, let's say, object detection or solving any problem. Self-driving car needs clear lighter clouds for. So it means that there are two kinds of 3D labeling problems. First is object detection, and second is cloud segmentation, when we are trying to find not just object, but are trying to classify every point in lighter cloud to find out something we are interested in. And here is an example of how the world is seen through self-driving car sensors. On the left side of the slide, we can see a lighter cloud with pedestrian and transport objects detected by a car. And on the right side, we can see photos. And on these images, we also see that every object of the interest, like transport and pedestrians, are detected and outlined with bounding boxes. Now let's have a look a little bit in details how 3D pedestrian labeling is working in our pipeline. The approach here is a little bit different, and this part of our discussion will be like storytelling. I'll try to tell you how the evolution of labeling techniques helped us to get better crowdsourcing performance quality and get better results on further usage of the labeled dataset. So the pipeline in general seems just the same. We ask what objects are presented on the image, then locate every object of pedestrian with a bounding box, validate this, classify, and then come to 3D labeling. And the idea of 3D labeling for pedestrians was from the beginning of this history of pedestrian labeling was a little bit different. We tried to find other approaches in order to get the labeled data faster, and we decided to make the following thing. When we have every pedestrian object outlined with bounding box on the image, we can take LiDAR cloud points which are projected on this bounding box, just like it is shown on this image. We have a bird eye view on the road situation here. We have a self-driving car, we have some man, we take some pyramid from the LiDAR cloud, which is projected on the bounding box on image, and then ask performer to find the minimum distance and the maximum distance. So it means that we are trying performer to choose the slice in this pyramid, the size of the slice and the location of the slice, which is reflected from the pedestrian object. So we have all the images labeled, take every bounding box, project images, project points from LiDAR cloud on this bounding box. We have during this projection, we get some pyramid from LiDAR cloud, and then ask our performers to find the appropriate slice in this pyramid. Looks great. So something like this. We have an image, we have a bounding box, we project points there. We have some pre-processing of this data. We use some algorithms in order to get rid of the points which are absolutely not reflected by a person. For example, on this slide, we can see an image where a pedestrian comes near to building wall, and these two lines of points which are presented in the bounding box in you can see it with the red and this blue color, are absolutely sure reflected by the wall. We can find these points because they are well approximated by surface, and just get rid of them and make the data clearer and help our performers to get better results. When I say performers, I mean someone who is using crowdsourcing platform to solve our tasks. And this is how the interface looks like. We have an image, we have a bounding box, we have LiDAR clouds points projected on this bounding box, and we have two views of the pyramid. This LiDAR cloud from the above and from the left side, I think, or from the right side, doesn't matter actually. So looks great, seems quite easy. It was fast, it was nice, it was cheap, and we were not disappointed by the results we got using this approach. And then we tried to visualize these results using our simple approach when we have a LiDAR cloud and just segmentate points of pedestrians. And here we have an example. This is some real situation, a road, people crossing this street, and with white color, these people are colored. Well, not bad. But after more attentive look on this type of data, we found out that we have some problems actually. For example, here we have an example where a pedestrian is standing near a car, and using this approach with slicing a pyramid comes to choosing not only pedestrian points but also parts of the car. And then we found out that sometimes our approach doesn't work at all. For example, here in the left side of the image, we can see that the person is occluded by a column, is standing behind the column. And when trying to solve this task, choosing a slice, for a pedestrian, our performers usually choose not a person, not a pedestrian, but a column. It means that something went wrong, actually. So using this approach, we managed to reach some quality metrics which were enough for our technology at that time, but then we found out that we have some problems, and we decided to use another approach, and now we do something like this. We just show our performers a full LiDAR cloud and ask them to segmentate points of pedestrians using simple and understandable instruments. It helps us to give more 3D context. It helps us to avoid problems with occluded objects, and it helps us to get higher accuracy and higher quality of labeling. So this is how we changed our approaches during technology improvement in order to get rid of some problems we can face during data labeling. And a little bit of discussion about this approach's evolution. 3 questions we have to pay attention to now. First of all, what is changed? It seems like we have changed only the interface of our task, but actually not only the interface, but all the back-end data processing procedures were changed. Metrics calculation, answers comparison, data format, databases for this labeled data sets, and so on and so forth. So when you are trying to change your data labeling approach, don't forget to calculate what you will have to change also with this interface changes. What are the circumstances of this changing? So as far as I have already said, the circumstances are, first of all, quality improvement, and that's all. Just quality improvement. But the labeling process became slower, the labeling process became more expensive, and we had to find a huge amount of time in order to build all the backend processes for this new format labeled data. But it means that if you are trying to build a baseline solution and you do not have to get a absolutely clear and absolutely fine labeled data set, you can use any approach you want just in order to get some labeled data just in order to start some labeling process, active learning process. But if you are trying to, I don't know, build last mile solution, you have to think about improvements and you have to think about the circumstances these improvements will bring. And what is the profit? So the data is clearer. We have something we can rely on. That's the main profit of this evolution of labeling processes. And the last example of video labeling we wanted to show you in our today's discussion. I mean, the last example of data labeling we wanted to show you during this discussion is video labeling. So when we are talking about computer vision problems, we are not talking only about frames. We're not talking only about single images. We can also need image sequences. Examples of tasks where you may need information about frame sequence and not only single frames are, for example, object tracking. It is when you detect an object in your, let's say, image, and you want to find his, for example, trajectory, or you want to find the same object in a few seconds, not only on this frame, but in some frames in the future. This is where you may need object tracking. For example, take a frame sequence and detect the same object on the sequence in order to get some time-dependent information about this object. And the second example of the situation when you may need video labeling is periodical processes. For example, it can be traffic light blinking, or it can be car light blinking, just when cars on the road use left or right traffic light in order to show other agents of road movement about to show them where this car is trying to turn on the left side or on the right side. And we will show you now some example of traffic, I mean car light labeling. So the main idea was, this is how the interface looks like. The main idea was we show our performers just a fragment of video with, I don't know, 5 seconds long maybe. It depends on the problem you're trying to solve. And in this video, we have a transport object outlined with a bounding box, and the performer has to ask the question, has to label its car lights state. So it's something like you have an object outlined with a bounding box, and for every frame in the video, this the performer has to determine the state of his car light, the left one and the right one. And as a result, we have something like this. Here we have a big truck outlined with a bounding box, and on the slide we also have this graph which shows us the state of both left and right car light. The blue color is about the, I think, the right, the left car light. The orange one is about the right, and 1 means here that the light is on, 0 means here that the light is off, and -1 means that we cannot see the light now. And this is how the result looks like. I'm sorry. So just some cyclogram of car light state. And you may need such type of labeling also when you are trying to determine traffic light state, because sometimes when you're driving and you see that the green light is blinking, it means that in a few seconds it will become red, and you have to start stopping. And these moments of road movement is quite important, and you have to determine them accurately. So this is the end of today's discussion. Some conclusion. First of all, we said that, of course, we have some open data sets for machine learning problems solutions, but sometimes when you have to face some circumstances which are not presented in these open data sets, for example, rainy weather, snowy weather, misty weather, I don't know, anything else, you have to collect your own data, and you may collect it yourself, or you may use crowdsourcing platforms in order to collect this data. But when you ask crowdsourcing performers to help you to get the data you need, you have to describe the task in details, not just only make a photo of the road, but describe everything you want to find there. Then we had a look of how the labeling pipeline for self-driving cars data is organized, talked a little bit about active learning process. This is when you're trying to find cases where your models are not good enough in order to get them labeled and use them in your learning process. Then we have had a look on transport labeling pipeline with 2D and 3D labeling using post-verification processes. Then we had a look on the evolution of approaches for pedestrian labeling, from the very simple but not well enough from the point of quality to quite difficult and long and expensive, but not ideal, but very good, talking about them levels of quality. And in the very end of our discussion, we had a slide look on example of video labeling and a little discussion of when you need it and why you need it. So this is the end of this video. If you have any questions or some interests, please join our Slack channel. Bye-bye.